Let's continue working some examples about finding double integrals or using double polar coordinates to find volumes and things like that. So our first example here is going to be problem 22. We're trying to find the volume of a given solid. And they're telling us we want to look at the sphere, x squared plus y squared plus z squared equals 16. That's the sphere centered at the origin with radius of 4. But we want to be looking at outside the cylinder, x squared plus y squared equals 4. Let's actually get a picture of what we're dealing with here. So we have x squared plus y squared plus z squared is equal to 16. Got a nice sphere there. But then we have x squared plus y squared equals 4. That's a cylinder that's cutting through our sphere. And essentially we're using that cylinder to essentially cut out a hole. We don't want to include the part that's inside that cylinder, so we have a hole through our sphere. We want to find the volume of the part that's outside that cylinder. I like to think of this as kind of like a napkin holder or something like that. So how are we actually going to set this up as a double integral? Well, I guess first of all we should note, actually I can't really see it very well from above, but the region that we're going to be integrating over is everything that's going to be outside of the cylinder. So everything is outside the circle of radius 2, but the sphere goes out to a radius of 4. So we could say our domain of integration is an annulus, where the inner radius is 2 and the outer radius is 4. In fact, we could write this as r equals the set of all points r theta, where theta is going to go all the way around the circle, so from 0 to 2 pi, but r is going to be restricted from 2 to 4. And now we need to know what function are we integrating, because the thing that we're integrating, we're trying to find the double integral of, is the sphere. If we were to set this up as in terms of x and y, we'd essentially solve this for z. So z would be plus or minus the square root of 16 minus x squared minus y squared. Move the x squared and the y squared over to the other side, take the square root. We do have a plus or minus because we could actually maybe use symmetry here and only find the volume above the xy plane, or we can just multiply by 2, or we can subtract these two functions. I'm going to go ahead and essentially double it. So here it's going to be double integral over r of 2 times the square root of 16 minus x squared minus y squared. But when we're working with polar coordinates, remember x squared plus y squared is r squared. So when we actually set this up as in polar coordinates, we're going to be integrating 16 minus r squared under the square root. Our limits, again, our theta is going to go from 0 to 2 pi. R is going to go from 2 to 4. And then remember we need that extra r and the dr d theta. One nice thing here is that we do not have any thetas in our integrand or our limits. Like I told you before, that was going to be a fairly common thing to have happen. So we're just going to basically end up taking the integral from 0 to 2 pi d theta as a 2 pi out in front. I'm actually going to go ahead and leave the 2 inside there for a moment. But we're going to have a 2r and a 16 minus r squared dr. Now how do we do this integral? I'm going to make a substitution. U equals 16 minus r squared. That means that du is negative 2r dr. That's why I wanted the 2 in here. We have this 2r already. We don't have the minus sign, but we can introduce a minus sign pretty easily. This is going to be the square root of u du. And our limits, well, when we plug in 2 and 4 into our formula, when we plug in 4 specifically, we get a nice 0. When we plug in 2, 16 minus 4 gives us 12. We go ahead and integrate the square root of u. Remember, that's u to the 1/2 power. So we raise that 1/2 power by 1 to get a 3/2, and then we divide by the new power. Plugging in 0 gives us nothing. Plugging in 12 gives us, well, it doesn't really simplify right away, but one thing to note is that we are subtracting it, so it's going to get rid of the minus sign. You get 2 pi times 2 over 3, and I'm going to write 12 to the 3/2 power as 12 times square root of 12. Because then I can go ahead and actually simplify some stuff. First of all, the 12 divided by 3 is just going to be 4. So I'm going to have a 4 times 2 times 2. That's a 16. So you can write this as 16 pi times square root of 12. Or you can even note that 12, we can pull out a 4 and end up multiplying the outside by 2. Wait a second. Instead of 2, we need a 3 here. There you go. So 32 pi times the square root of 3. That is the volume in this napkin holder. Well, I'm just going to keep calling it that. Problem 27 is actually pretty similar. This time we're still using exactly the same cylinder that we were looking at before, but now we're looking at an ellipsoid, and we want to find the volume that's inside both of them. So if we go back to our graph here, we're not using the sphere anymore, but we do have the ellipsoid. That was 4x squared plus 4y squared plus z squared equals 64. I'm going to zoom out a little bit here. So we want to essentially take the intersection of these two things. Maybe that's a little hard to see exactly what it's going to look like because everything's inside of the ellipsoid. So maybe I'll actually kind of cut out the things that we don't need. So by using a couple little techniques, I managed to cut out the portion of the ellipsoid that is on the top and bottom, and then look at the portion of the cylinder that's between those two pieces. Say we have kind of a, I don't know, we'll say it's a hot dog. And we're trying to find the volume that's inside that thing. Now, of course, what we're doing here is using that cylinder as our base. So we're looking at the stuff that's inside the disk of radius 2. In other words, we write out r, it's going to be the set of points of r theta, where theta can go all the way around the circle, but r is only from 0 to 2. Now, what is our actual function that we're dealing with? Remember, we are looking at the ellipsoid as our function. We need to solve for z. You can say that z is, well, plus or minus the square root of 64 minus 4x squared minus 4y squared. In fact, if we want to, we can pull out a 4 from inside there. So plus or minus 2 square root of 64 divided by 4 would be a 16 minus x squared minus y squared. In polar coordinates, remember x squared plus y squared is equal to r squared. So in polar coordinates, we'd use z is plus or minus square root of 16, or 2 times the square root of 16 minus r squared. So we're gonna have this square root in there again. Let's actually move this over so I can have a little more space. Our volume is going to be a double integral over this region of this function. Well, not of this function really, because remember, we are going between two different functions here. So this minus the negative version of it ends up doubling. In fact, let's go ahead and use this formula here. So we're doubling that 2 to get 4. Then we have 16 minus x squared minus y squared dA. When we put that into polar coordinates, our theta is going from 0 to 2 pi. R is going from 0 to 2. We have 4 times the square root of 16 minus r squared. We have that extra r in there. Don't forget that part. Then we have dr d theta. And in fact, a lot of this is going to work out very similar to how it worked out in this particular one back here. Because we have the r times the square root of 16 minus r squared, and we have the exact same thing here. First thing before we even get to that, though, is, again, we don't have any thetas inside here, so that part just becomes a 2 pi. But I'm actually going to go ahead and pull out a 2 from that 4. So we'll end up with a 4 pi on the outside. And we're integrating 2r square root of 16 minus r squared. We made the substitution of u equals 16 minus r squared. That means du is negative 2r dr. We end up with an extra negative out here, but then everything in there just becomes the integral of square root of u. Our limits this time, when we plug in 0 and 2, plugging in 0 just gives us 16. Plugging in 2, in fact, is what we did last time. We got 12. So we have a negative 4 pi times we have u to the 3 halves times 2 thirds from 16 to 12. So we get 4 pi times 2 thirds times 16 to the 3 halves power. Well, that basically think of 16 square rooted is going to be 4, but then cubed is going to be a 64. Then minus 12 to the 3 halves. Again, I'm going to write that as 12 square root 12. And if we want to, we can go ahead and simplify things. For one thing, we can actually pull out a 2 from this 12 and make this into a 24 on the outside. But then 64 and 24 are both divisible by 8, so I can pull an 8 out. On the outside, we already had a 4 times a 2, so we already had an 8. So we'll have a 64, a pi, and over 3. When we pull out an 8 from the 64, we're left with 8. When we pull out 8 from here, we're left with a minus 3 square root 3. And there's not really any better simplification of that. I mean, you could try various things, but I don't know if there's any nicer way of writing it. And of course, that's the volume inside this hot dog. Now, one last example that I want to go through is essentially contained in problem 40, though I'm going to approach it a little bit differently than they do in that problem. I don't really like where they start it, because they don't really motivate why they're doing any of it. What we're really going to be looking at is the integral of e to the minus x squared dx. Now, you might have heard that this is an impossible integral to do, at least in terms of elementary functions. And that would be correct. But if we graph this integrand, so let's go ahead and actually open up GeoGebra again. We're graphing the function f of x is e to the minus x squared. We have this curve here. And you may actually recognize this curve, or at least have an idea of what this curve is used for. This is what we frequently refer to as the bell curve, and it's a very frequently used thing in statistics. Now, in various statistics applications, they'll use various transformations of this, various rescalings of things. But this is the base curve that everything is comes from. And so this is a very important curve to use. And specifically, finding areas under this curve is a very important idea in statistics. We're not going to be able to give some general formula for any area that we want to talk about. In fact, they don't. They usually just use numerical integration to actually get estimates for various areas. But what we can do is find the area under the entire curve. So note that this curve never actually does hit 0, but it does go to 0 fast enough on both sides that it only has a finite area underneath it. This improper integral does converge fairly easily. And we want to find out what is the exact value of this improper integral. But how are we going to do that without being able to find an antiderivative of e to the minus x squared? We're going to use a little bit of a trick that actually becomes possible thanks to this section. First thing I'm going to do is I'm just going to name this integral. I'm going to call it I. And then we can work with the value I and not have to necessarily come back and write this integral every single time. The next thing I'm going to do is I'm going to square it. What is I squared? I squared is this integral times itself. And I'm just going to write that out. We're going to take this integral, and we're going to multiply it by another copy of the same integral. Except this time around, I'm going to change the variable. Instead of using x's, I'm going to use y's. So I have the product of two integrals, and because I'm using x and y, I can think of these as two parts of a double integral. Remember, if we have a double integral where we just have a function of x times a function of y, we can split this up as an integral over x times an integral over y. Well, we're going to do the opposite here and actually combine these together so that we have the integral from minus infinity to infinity, same kind of thing. Then we have e to the minus x squared times e to the minus y squared dx dy. Now, it might feel like we're making things much more complicated, but it will get better. The important thing here is, what are we actually working with? We're working with a double integral. This integrand can actually be written as e to the minus x squared plus y squared. And what is the domain of integration? What are we really talking about when we're letting x go from minus infinity to infinity and y go from minus infinity to infinity? Well, we're just looking at the entirety of R2, the entire plane. That's what we're trying to do. We're taking this function e to the minus x squared plus y squared over the entire plane. Let's actually even graph that thing. So we're going to essentially take this curve here and look at a three-dimensional version of it. So we're going to say f of xy is equal to e to the minus x squared minus y squared. I didn't factor out the negative this time. And we get this surface here, which is essentially mostly flat, except technically not. None of this actually ever hits the xy plane. It's always just slightly above it, but there's kind of a bump in the middle. There is a finite volume underneath that curve, or underneath the surface. And we want to find out what that volume is. Now, how are we going to do that? How does any of this really help? Well, there's a reason why we're doing this integral in this chapter. What if we change this to polar coordinates? And how would we describe the entirety of the plane in polar coordinates? Well, in polar coordinates, we might say that R2 is a set of all points r theta, where we'll just take theta from 0 to 2 pi, because there's no reason in going around the circle more than once. And then r, we can start at 0 and go off to infinity. Now, we're playing a little fast and loose with improper integrals here, but I don't want to get into the nitty-gritty of all this stuff. Everything does work out nicely. But the important thing here is, if I put this into my polar coordinates, take theta from 0 to 2 pi, r from 0 to infinity. Remember, my integrand is e to the minus x squared plus y squared. X squared plus y squared is just r squared, so that's actually very nice. We have e to the minus r squared, which that doesn't look very nice right away. But remember, we do have the advantage that we get an extra r. And that extra r is actually going to make everything possible. Because that extra r is actually going to allow me to make a substitution. Well, first things first, the fact that we have the d theta with no thetas in the inside just means I can pull out this integral as a 2 pi. This part, I'm going to make the substitution of u equals minus r squared. That means du is negative 2r dr. Well, we don't have the 2 initially, but actually we can kind of steal it from the 2 theta or the 2 pi that we have outside. So the 2 from the 2 pi will combine with that r. We will get a minus sign, but we'll have e to the u du. If we plug in 0 and infinity into negative r squared, obviously 0 is going to give us a 0. As r goes to infinity, u goes to negative infinity. Again, really kind of playing fast and loose with those improper integrals, but it works out nicely enough. Now we take the integral of e to the u, which is just e to the u. When we plug in our limits, e to the minus infinity, well, we're really looking at the limit as u goes off to minus infinity of e to the u, but that is just 0, if you remember how exponentials work. So that minus pi times 0 minus what is e to the 0 power is just 1. So we end up with pi. A very nice, simple result. And what does that mean? Well, that is I squared. But remember, I is the integral from minus infinity to infinity of e to the minus x squared dx. So this integral is the square root of I squared, or it's the square root of pi, which you probably wouldn't expect. Why did something that just involved the exponential function end up being entirely expressed in terms of pi? Again, kind of skipped over a few technicalities with regards to improper integrals, and it's possible to make this all formal if we really cared to. But the point here is that we did get the correct answer. And it was all thanks to being able to work with polar coordinates. So hopefully you can see at this point that how we can use polar coordinates to make a number of integration problems a lot easier, including ones that may not have looked like they involved polar coordinates in the first place. In the next section, we will actually get into some applications. We've kind of wouldn't want to say we've run the course on how to work with double integrals, but we do want to see how we can use them more than just finding volumes. So just like with regular integrals, there are a number of things that we can do with double integrals, and we want to see what the possibilities there are. So I'll see you guys in the next section.